Okay, I want to talk about circular motion, and of course we have the beam, and we rotate it like this. Any point of the beam, this is what I want you to focus on, any point of the beam moves around a circle. The radius depends on how far it is from the center. So you might think of any one of these magnets. Of course, the magnet covers an interval of distance from the center. But if you just kind of think of the center of the magnet, you can see that the center of the magnet, at least, and any point on the magnet, in fact, describes a circle. Different points will describe a circle of different radii. Okay. So here is an approximate circle. It kind of lost its mind down here. The rest of it's pretty good. You understand what it represents. And we're going to postulate a center. And I assume we know the geometry of a circle. Things like, for example, any radial line is perpendicular to the tangent at that point. Now, it's not a perfect circle. I don't think I have a perfect right angle there, but we understand that that's the way it is for an actual circle. And we're going to say that any point on the circle has an angular position that's indicated by the angle, which I'll call theta, between the positive x-axis and a tangent line. Now, implicitly, the origin of the coordinate system I'm using is the center of the circle. So we have an x and a y coordinate. Also, if we know the angle theta in the radius of the circle, which I'll call A instead of R, and we'll understand fairly soon why I use A for the radius. Okay, then this point has coordinates A cosine theta, A sine theta. And this projection here has a displacement from the origin, not a distance, a displacement of A cosine theta. Why do I say displacement instead of distance? Well, the distance is the magnitude of A cosine theta, but A cosine theta is negative in this case. It'd be positive if we were on the first or the fourth quadrant. If the point on the circle is on the first or the fourth quadrant, it's negative if the point on the circle is in the second or the third quadrant, as you should know very clearly. Okay? And then this point here has coordinate A sine theta. I didn't really leave myself room to label it, but I could draw an arrow from here to here, and this arrow would indicate the displacement A sine theta. Okay, well, there's much more. We're talking about motion on a circle. Okay, so if the point is moving around the circle, and let's just take a point down here in the third quadrant. Now, some of these labelings are overlapping. Didn't plan it out well enough, but you get the idea. Okay? So this point, now I've drawn an arrow from this point to this point. Okay? And I could say that this vector, which I'll call R, is A cosine theta times the I vector. The I vector being, I hope you're familiar with this, being a unit vector in the positive x direction, a vector of length 1 in the positive x direction. Because of what I just said here about these displacements, the r vector is A cosine theta times I, A cosine theta would be a vector from about here to here. Okay, A cosine theta I would be a vector from about here to here. And A sine theta j would be a vector from about here down to here, wherever the projection of this vector hits the y-axis. So there's your vector r. Now, if the point is moving, then the motion is described by, first of all, the parametric equations. Well, actually it's not a parametric equation. Theta of t, okay, equals, now we're going to say this is equal to omega of t times t, where omega is considered to be a function of time. So for example, if the speed or the angular speed of this point is increasing, then omega of t would be an increasing function of t. Okay? And if it's decreasing, omega of t would be a decreasing function of t, meaning, of course, that, okay, well, let's just say y, theta prime of t equals what? Well, it's a derivative of omega of t times t, right? So that would be omega prime of t plus omega of t. Okay? Derivative of the product function. You have an omega prime plus an omega. Okay, now, and of course then you could have a theta double prime and all that stuff. Omega of t equals constant, and we'll write that just as omega. Then theta prime of t just equals omega. And that's the first case that we're going to look at. Now you know when the system that we've studied rotates, the beam on the strap with the magnets and all that, we know that it slows down. That's one of the first things we measured. One of the first things we measured then, well, one of the first things we observed, a graph you'd be familiar with is omega, where you have omega versus t. For the beam. Now, omega changes. Okay, you have an omega prime, and maybe we ought to say this is omega of t to emphasize it's not a constant omega. Okay, so omega of t appears to be a linear function. Omega of t is linear, just to bring this back to something that we've observed and analyzed with some thoroughness. Okay? So now we know what omega is. Okay, well, now we want to know just what the velocity of a point is. Okay, so, and let me color code this. So this is going to be v of t. Okay, now let me back up. I should have said then, well, I've already said it, that theta of t equals omega of t times t, which we can abbreviate as theta equals omega t, but if omega is a function of t, we might want to write the t dependence to remind ourselves of that. Okay, well, our position r of t, r is a function of t, and I said it's a cosine theta I plus a sine theta j, but now theta is some function of t. Okay, so r of t is going to be a cosine of omega of t times t plus times the I vector plus a times the sine of omega of t times the j vector. Okay, so that v of t, and I'm declaring this without deriving it, and this is something that's derived in multivariable calculus early in the course, and it's pretty easy to understand, and I'll justify it in a little more detail later, but intuitively, velocity is the derivative of position. The position is described now by the vector r. The rate at which r changes is r prime of t, and that equals, well, in general, it equals the derivative of the inner function, which is omega prime plus omega times the cosine of this function, and by the chain rule, similar for this. So we can write this, and you should verify this. This is omega prime of t plus omega of t, and we'll keep the a out here. All this factors, because the a is common to both terms, and so is the derivative of this inner function, which is the same for both the I and the j components. So it's this times negative sine of omega of t times t plus the cosine of omega of t times t. Okay, well, that's the general form for the velocity, and you also have an acceleration function. Now, in analyzing the motion of this strap, omega, again, is a function of t, and we think it's a linear function of t. So we could actually calculate these. And we could easily calculate this. Interpreting it may be a little bit challenging at this point. A of t, though, is something you can calculate, and that's going to be homework. Okay, just calculate the A of t, just an exercise in calculus. Now, the simplest situation is where omega of t is constant. We have motion around a circle at constant angular velocity. In that case, omega prime is 0. So, and you can easily see that this is just omega times t, where omega is a constant. You're just going to get an omega out in front here instead of all this. So this will be 0. This will just be omega if we suppress the t dependence for the constant angular velocity. Okay? And this expression becomes much simpler, and so does the expression for A of t. So now r is a function of t, but I don't have a lot of room, so I'm going to okay, so r prime it's just going to be the derivative of that, simple enough. And A equals V prime equals R double prime, which equals negative omega squared A cosine of omega ti plus sine of omega t j. All very simple, very easy to verify and to check whether I'm making a mistake with this. Okay? That's certainly possible, you know that. Okay, so there we have it. Now, in this case, this should remind you a lot of what happens with simple harmonic motion, where we just take one component of the r vector, the I component, say, and of course we might have a phase angle phi on it, but these derivatives should remind you completely of the derivatives you get there, except now we have two components. Okay? Now, we then conclude that A equals negative omega squared r. Okay? That V is orthogonal to R, and V is orthogonal to A, neither of which would be true in the general case, which I might ask you to verify. And that's probably enough for right now. Okay, so we know that for constant angular velocity, this is orthogonal to this. And also for constant angular velocity, your acceleration, which is in the opposite direction to r, it's negative omega squared r, okay, is also orthogonal to v of t. And this is toward the origin if omega, again, is constant. Okay? So there is a picture of uniformly accelerated motion, of motion around a circle at uniform velocity, angular velocity, or uniform speed, v. And my digression caused me to forget what I said before. But yeah, again, it's your model for motion around a circle with constant angular velocity. Now, if omega was negative, you'd be moving this way. If omega is positive, you move this way. And of course, you want to be able to verify that in terms of these functions.